Okay, so we're going to cover the last section of Chapter 7, Molecular Structure and Polarity. So within this section here, they specify the bond angle, so it's important to understand what the definition for bond angle is. So it's the angle between any two bonds that includes a common atom. Okay. And then you have bond distance. So bond distance is the distance between the nuclei of two bonded atoms along a straight line joining the nuclei. So bond length and bond angle is something that we're going to be talking about in this section. And so bond distances can be defined in angstroms or picometers. Angstroms is normally what's used when you're talking about bond distances, and that's defined as 1 angstrom being 1 times 10 to the negative 10th meters. And then the bond angle is also important too, because that's indicative of the molecular geometry for the molecule. So we've learned how to draw out the Lewis dot structures for different compounds, and that kind of goes hand in hand with molecular geometry. So for example, you may have to figure out the Lewis dot structure for a compound and then figure out its molecular geometry. And so they sort of go together in a way. So we need to learn a little bit about VSEPR theory. So VSEPR is an acronym for valence shell electron pair repulsion theory. So that enables us to predict the molecular structure, including the bond angles, for a molecule. All right, and so it's indicative of the number of bonds and the number of lone electron pairs in its Lewis structure. So drawing out the correct Lewis structure, of course, is vital in order to be able to predict the molecular geometry for the molecule. So here we have a picture of the Lewis dot structure for beryllium fluoride, so BF2, BeF2. And the molecule here adopts a linear structure, okay, which is referred to as it's just linear. The bond angle there is 180 degrees. So we'll learn how to, there's some things you have to memorize in order to be able to predict molecular geometry. And so it's part of these tables here that you're going to have to memorize. So here this table represents what's referred to as electron pair geometries. And so you're looking at, if you notice, you're not going to see any lone pairs on the central atom in this case. Okay, so this is basically when you have no lone pairs on the central atom. And so if you have two regions of high electron density, okay, this is referred to as a linear arrangement here. Okay, so the electron pair geometry would be referred to as linear. If you have 3 regions of high electron density, that's referred to as trigonal planar, okay, electron pair geometry. Again, notice there's no lone pairs on the central atom. When there are 4 regions of high electron density, this is referred to as tetrahedral. Okay, and notice the angles are all different too. Linear, the bond angle is 180 degrees. Trigonal planar, it's 120. Tetrahedral is 109.5 degrees. And then when you have 5 regions of high electron density, that's referred to as trigonal bipyramidal. Okay, so trigonal bipyramidal, you have this, in this single plane, you have 3 atoms there on the single plane, and then you have an atom going up and then down from that plane. And so you have some angles that are 90 degrees from one another, bond angles, and then you have some bond angles. The ones that are on the same plane are 120 degrees. And then you have, when you have 6 regions of high electron density, that's referred to as octahedral. So octahedral, instead of having 3 atoms on the same plane. You have 4, kind of makes like a square base in a way. And then you have an atom going above the plane and then below the plane. Okay, and that's referred to as octahedral in terms of electron pair geometry. So what I wanted us to do is look at PhET simulation here. And you can actually, if you wanted to, you could look at this as well online. Okay, it's free for you to look up online. Here's the web address. Okay, so you can look that up. Whenever you get to this page, all you do is click download. Okay, and then this page is going to pop up. Now, the default page is showing it's on model here. Actually, it's going to ask you to choose between model and real molecules. So I'm going to be using real molecules. Okay, and then there's a drop-down list. Okay, so I wanted to show you examples of the ones we just looked at. So electron pair geometries for linear, for example. I know you can see this picture here, but sometimes it's better to see it in 3 dimensions. And so an example of a linear molecule would be CO2. And you see the bond angles here at 180 degrees. And you're just able to see, well, this looks like a straight line. It's a linear molecule. Okay. And so that's when you have 2 electron pair geometry, basically. Your electron pair geometry is 2. Okay, you have 2 electron pairs here. Okay, not including the central atom, there's 2. And so it's a linear arrangement. When you have 3, it goes back to trigonal planar. So this is what it looks like here on the table. And then BF3 here, this is trigonal planar. So notice that the 3 atoms here are on the same plane. Okay, to me it kind of looks like a Mercedes sign. Okay, if you think about like the Mercedes sign, it kind of looks like, has this shape to it. Bond angles are 120 degrees. I mean, you can move it around, but it's going to be reset to 120 degrees for all the bond angles here for this molecule. All right, so that's trigonal planar. Okay, and the next type we have is tetrahedral. All right, so tetrahedral, an example would be methane. So you can see tetrahedral, it kind of looks like a little tripod with a little head on the top, maybe. And all the angles for tetrahedral are 109.5 degrees. All right, tetrahedral. So notice that's with 4 electron pairs. There, 1, 2, 3, 4, excluding the central atom. And then when you have 5, that's trigonal bipyramid. This is what it looks like here on this graph, trigonal bipyramidal. And then using this PhET simulation here, it's PCl5. So this is trigonal bipyramidal. So you see that trigonal's 3, right? So you have 3 atoms. It's sort of like trigonal planar. Remember when it had 3 atoms and it sort of looked like a Mercedes sign? That's on one plane. And then you have an atom going up and an atom going down. So trigonal bipyramidal means trigonal is the base. You have a base of 3 atoms. And then if you drew lines to this top atom here, it would look like a little pyramid. Okay, and you have that case on both sides. So you have a pyramid at the top, and then you would have a pyramid at the bottom, again with these 3 being the base. So trigonal bipyramidal, 2 pyramids, one on top, one on bottom. And then the last one, when you have 6 electron pairs, that's referred to as octahedral. So with octahedral, you have, instead of a base of 3 in the same plane, you have a base of 4. So an example of that would be SF6 here, and you see we have a base of 4, 1, 2, 3, 4. They're in the same plane. You can see that. So those 4 atoms are in the same plane right here. Okay, so they're in the same plane. And then you have an atom going up and an atom going down, and this is referred to as octahedral. Your angles there are all 90 degrees. Okay, an octahedral. So that's when you have 6 electron pairs, excluding the central atom. All right, so next we need to learn how, so far we've just talked about molecules that have no lone pairs. But what you'll find is when a molecule has a lone pair, it affects the geometry, okay, greatly. So let's talk about this. Your book talks about electron pair geometry versus molecular structure. So we've talked about electron pair geometry, and that's whenever the central atom has no lone pairs. Molecular structure is different, though. So molecular structure is going to be the actual structure of the structure relative to the atoms in the structures and not the electrons. And so with electron pair geometry, we're talking about, the number of electron pairs. In this case, the assumption, though, is you don't have any lone pairs. Okay, but molecular structure can vary, and especially whenever you have lone pairs, it affects the structure of the atoms in their orientation. And so we have to learn both of those. So I refer to as electron pair geometry sort of as the parent. Okay, and then when you start to add lone pairs, then its structure is going to change. Now, if you don't have lone pairs, electron pair geometry and the molecular structure are going to be the same. But if you do have lone pairs, that's when the molecular structure and the electron pair geometry can differ. Okay, so we know, for example, that there are some compounds that have lone pairs on the central atom, like ammonia, for example. And its molecular geometry is not going to be the same as any of these electron pair geometry structures because it has lone pairs. Okay, so we need to know what kind of geometry you're going to expect when you do have lone pairs. So here we see an example of methane, CH4. It has electron pair geometry of tetrahedral. It has 4 electron pairs. Okay, it has no lone pairs on the central atom. So its electron pair geometry and molecular structure is the same as tetrahedral. Okay, but when we have something like ammonia, for example, when we have a lone pair, that is going to have a different molecular structure. Okay, it still has, now ammonia still has 4 electron pairs. Okay, it has, so ammonia is NH3 is the formula. So when you draw out the Lewis structure, it has 3 hydrogen atoms that the nitrogen has a single covalent bond for 3 nitrogen atoms, and it has a lone pair. So that's 4 electron pairs. But it only has 3 bonding pairs. Okay, so that affects the angle. Okay, it's no longer 109.5 degrees like a tetrahedral structure would be. Instead, it's 106.8 degrees for the bond angles. And the reason for that is because of the lone pair. The lone pair basically has a greater repulsion than a single covalent bond or even a double or a triple. Okay, it takes up more space, and so what it does is it pushes these bonds and makes them smaller from 109.5 to 106.8. It pushes them down. Okay, and so we need to look here at so this molecular geometry is different, and so for ammonia, its molecular geometry is trigonal pyramidal or trigonal pyramid compared to tetrahedral. And so, and that's true because it has that lone pair. So we see here the, if we were to rank with Vesper's theory, the theory is with electron pair repulsions, the greatest strength of electron pair repulsions has to be from a lone pair interaction. And that's greater than a lone pair bonding pair or a bonding pair interaction. So what we're saying is if the molecule has a lone pair, it's basically going to force the other bonds, whether they're single, double, or triple bonds, to get closer, because a lone pair takes up more space than a triple bond does, and it takes up more space than a double bond, single bond, etc. So you can see that ranking here. The lone pair takes up more space, occupies more space than a triple bond. And the triple bond occupies more space than a double bond. And a double bond occupies more space than a single bond. Okay. So now that we know that, we can go back and look at our electron pair geometries. Okay, when you have no lone pairs, and compare that when you do have 1 or 2 or 3 or 4 lone pairs. Okay, and so this chart is something you're going to have to memorize and know, because you're going to be having to draw out Lewis structures, and you're going to have to figure out what its molecular geometry happens to be. Okay, so if we look at the parent geometry or the electron pair geometry, we've already gone through that once. So we're going to go through that again, and then we're going to go through when we replace one electron pair with one lone pair, or two lone pairs, or 3, and see how the shape changes based off the lone pair.